Hi everyone, welcome back to Dave's Math Channel. I'm your host David Tare, and this is my continuation of the Math Lovers book feature I've been running for the last 5 or 6 months, I think. And I'm on chapter 6 of volume 1, which is on group theory. And I've been doing this for the last week or so. Now I'm on subsection 6.2.1. It's a pretty big chapter, and there's a lot of different types of groups. But right now, I'm talking about various types of symmetry groups of 2D figures. And so far, I talked about mirror symmetry. That was a couple lessons ago. Last lesson I did was on n-fold symmetry. That's the rotational symmetry of a figure with that looks the same if you rotate it by an angle of 360 degrees divided by n. For instance, regular n-gon has a symmetry. Today I'm going to talk about a third type of symmetry, and that's what's called dihedral symmetry. Kind of similar to n-fold symmetry, but it's got, I think I sort of mentioned this last time. The thing about n-fold symmetry is that figures with n-fold symmetry don't have to have mirror symmetry in addition. It's kind of a different kind of symmetry. But if you apply both symmetries, if you have a figure that has both mirror symmetry and n-fold symmetry, you end up with a figure with dihedral symmetry. And the group that describes this symmetry, or the groups that describe this symmetry, are known as dihedral groups. So anyway, that's kind of what dihedral groups are in a nutshell. But let's begin the lesson. So, yeah, I just kind of told you what a dihedral group is, and, like they say, picture's worth 1,000 words. This is the simplest dihedral group, and it's called, the letters we use for representing dihedral groups are dn. I think last time I mentioned that n-fold symmetry groups are isomorphic to Cn, the cyclic group of order n. Well, dihedral groups actually have Cn as part of their group structure. It's what's known as a subgroup. But Dn is actually a bigger group. And these are examples of non-abelian groups. These are the first non-abelian groups that I've discussed so far. And if you remember, I think I'd said what abelian and non-abelian groups are. Abelian groups are groups that are commutative with respect to group multiplication, meaning that b times a is equal to a times b for all elements of a and b of your group. Well, that's not necessarily true for non-abelian groups. You don't have to have commutativity. As a matter of fact, for the dihedral groups, you don't. There are elements, we'll see, that don't commute for dihedral groups. And how are we supposed to think about this group? So I showed an equilateral triangle on the bottom of this figure, and I think you can see that it has three lines of symmetry. The three lines shown, those are lines of mirror symmetry. So the easiest to see is the vertical line. If you reflect an equilateral triangle about the vertical axis, I think you can see it's going to look the same. But that's not the only symmetry axis. You've also got these two tilted ones, each at 60 degrees relative to the vertical axis. And similarly, I mean, if you reflected about these two axes, those are still symmetry axes, and would still look the same. But those aren't the only symmetries. You also have threefold symmetry. If you rotated this figure 120 degrees, either clockwise or counterclockwise, it would look the same as well. I've just described 5 symmetries of this equilateral triangle, but there's always a 6th one, namely the identity. And it turns out those are the only 6 symmetry transformations of this equilateral triangle. So the dihedral group, which we write as D3, has 6 elements. Another way to say that is it has order 6. I don't think I defined the order of a group yet, but it's kind of like the cardinality of a set. The order of a group is really just its cardinality if you think of it as sets. So the order of D3 is 6. In general, the order of Dn, I haven't talked about Dn yet, but the analogous group for a figure with n-fold symmetry, that has order 2n. It's always twice the rotational symmetry order. So anyway, so that's what D3 is. But now we want to kind of describe it algebraically. This is a little trickier. And like I said, it's a non-abelian group. And it's also not a cyclic group. Remember, cyclic groups just have one generator? Actually, this group has two generators. In general, every dihedral group has two generators. In that sense, they're more complicated than the cyclic groups, which just have one generator. So one of those generators is the same one you have for the cyclic group. I think I'll just stick with D3 for now. So one of those generators of D3 is the same thing we had for C3, namely A. It's the 120 degree counterclockwise rotation. And just like for C3, if you apply it twice, you get a 240 degree counterclockwise rotation, which is equivalent to a 120 degree clockwise rotation. And if you apply it 3 times, you get the identity. Just like for C3. So that's the algebra of A. But there's another generator, namely B, which is the reflection about the vertical axis. Because like I said, this group has mirror symmetry in addition to threefold symmetry. That means that there's a second independent transformation, namely the reflection about the vertical axis. And I think you can see that that is not generated by A, because A doesn't reflect. Rotations don't reflect. If this figure didn't have threefold mirror symmetry, I think you can see that the rotations make it look the same, basically just rotated, but they'd still look the same in a mirror. But if you do a mirror reflection of the figure, it looks different. That's if it didn't already have mirror symmetry. For instance, if this picture was a baseball mitt, A would just rotate the baseball mitt. If it was a left-handed mitt, it would stay a left-handed mitt if you rotated it by any angle. But if you reflect it, then it's going to turn into a right-handed mitt. So if you like 3 of these symmetry transformations, leave it alone, keep it as a left-handed mitt. The other 3 will turn it into a right-handed mitt. So and there's three reflections, like I said, reflections about any of these 3 axes. One of them we're calling B, the one that does the reflection about the vertical axis. Turns out you can generate the other 2 in terms of A. So let's just think about this a little bit. I think it's good to stick with a picture. What would happen if we followed the reflection of this equilateral triangle by a 120 degree clockwise rotation? That's A. Well, then you would end up, and I didn't really do this very well because you kind of have to label the vertices to see what's going on, but that would be equivalent to I think reflecting the figure about the axis that's sloped downward. And then if you followed B by A squared, you get the third axis. The axis is that's sloped upward. So that's going to give you the other 2 reflections. So the reflections, the transformations that correspond to reflections, are all the ones with B in them. B, AB, and A squared B. So those are the 6 elements of this group. But we still have to worry about the what happens if we do BA. And like I was telling you before, this is not an abelian group. BA turns out to be not equal to AB, but A squared B. Let's see how we can see that. If we first, so BA is where we first, remember we're going from right to left. This is another thing that's kind of confusing about group multiplication. You always proceed from right to left. So when we write BA, we're doing the 120 degree counterclockwise rotation A first. So first we're rotating 120 degree counterclockwise, and then we're reflecting about the vertical axis. Well, I think you can see that that's going to bring the point that started out at top to the bottom right. So that's going to correspond to the axis that's sloped upward. So that's the same as A squared B. So that's the algebra of this group. BA is equal to A squared B. And it's also true you can convince yourself, I'm not going to do it right here, but b squared, ba squared is equal to ab. So, but it's enough to know just this. The equation, the top equation I've written here for G, I'm just calling it G here. This is the algebraic notation of G. It has two end generators, A and B. Then the algebra satisfied by them is a cubed equals b squared equals e. Remember, b is a reflection, and every reflection has order 2. And a is a 120-degree counterclockwise rotation, which has order 3. So that's the first part of the algebra. A cubed equals e, and b squared equals e. And then the second part is just says ba equals a squared b, and that completely defines our group. And since G is isomorphic to the dihedral group of order 3, or D3, then we can say D3 is the same group as the group with the two generators A, B, satisfying the same algebra I just said. So anyway, and I think it's useful to show a Cayley table in this case. I haven't been doing this for the last few groups because they were kind of trivial Cayley tables. But for this one, I think this is a lot more interesting, a Cayley table. Like I said, this is a non-abelian group. One characteristic of abelian groups, if you wrote down their Cayley table, you would find that all the is that true? No, forget what I was going to say. Yeah, it's not true. But this is a useful table. I mean, if you just look at this table, you can use it to compute BA, for instance, and you see B is in the. You just look for the row of B in the column of A and see where they intersect, and you see that the element in that entry is A squared B. Or if you wanted to know, for instance, A squared B times B, well, the B's just multiply. That's going to give you A squared. But how about A squared B times A? You can look that one up. That's the bottom row in the second column. That's AB. And I actually do a couple examples like this in my book. You can do it either using the Cayley table. You can also do it algebraically. I think it's a lot harder to do it algebraically, but I do it here. I don't even know if I want to go through all the steps here, but yeah, the easiest way to do is with a Cayley table. Yeah, I'm not going to bother to go through all these steps because there's a lot of steps to compute BA squared, but it is equal to AB, which I've shown here. And second example is a little bit simpler. Maybe I will go through this one. What about BAB? Well, remember all groups are associative, so it doesn't matter how you group the terms. So we might as well do it this way. Do B multiplied by BA on the left. But we already know that BA is equal to A squared B because that's part of the algebra of this group. So that's equal to A squared B in parentheses times B. But again, by associativity, that's equal to A squared times BB, and BB is just B squared. So it's A squared times B squared. But B squared, since B is reflection, is equal to E. So that's just A squared times E. And we know that anything times E is the thing we started with. So that's just A squared. So this one is a little easier. But you can do any example like this that you want. And it's probably easier to do with the Cayley table. But anyway, so that's the group D3 and how it works. And you might wonder about a higher order dihedral groups, and you can do it from any order you want. And if you wanted to write down the algebra, I'm not going to derive this here, but it turns out it's very analogous to D3. We would call the dihedral group of a regular n-gon. This is the symmetry group of a regular n-gon. We call that Dn. And remember, like I said earlier, it has order 2n. It has, it has two generators. It has generators which we call A and B again. B is again reflection about the vertical axis, but A is now counterclockwise rotation by an angle of 360 degrees divided by n, or if you like 2 pi over n if you're working in radians. It's just the thing that rotates at 1/nth of the way around a circle. So if you do it n times, you'll get the identity, and that's what I say at first. So if you write down the algebra, you notice that a to the nth is equal to e. That's just saying if you apply the counterclockwise rotation n times, you get back what you started. You've done a full 360-degree rotation. And similarly, since b is the same thing we had before, b squared is equal to e. And then what about BA? Well, remember for the case D3 was equal to a squared. B in general is equal to a to the n minus 1 times b. I don't know if there's a really easy way to see that. I mean, just remember that b is a reflection. And once you reflect, if you start by rotating counterclockwise and then you reflect, maybe the easiest way to see this is that it results in a rotation of the reflected figure, but in the opposite direction, because you reflected afterwards. That means that it would have been the same thing you got if you started by rotating, if you finished by rotating clockwise rather than counterclockwise. So a to the n minus 1, that's the same as a to the minus 1, or the inverse of a. And if a was a 360 degree divided by n clockwise or counterclockwise rotation, then I think you can see that its inverse is a 360 degree divided by n clockwise rotation. So that's kind of the justification for this algebraic representation of dn. So that completes my discussion of dihedral groups. Thank you for watching. Long live math, and I'll see you guys next time.